Imagine walking into a plant room, right? And you find a massive industrial-grade fiberglass vessel, completely crushed inward.
Oh man, that is a gut-sinking feeling.
It really is. You are looking at a piece of equipment rated for 10 bar of internal pressure, but it has buckled like a cheap plastic cool drink bottle.
Right, and the crazy thing is the failure didn't come from an explosion. It didn't come from a forklift driving into it.
Exactly. It came from a completely invisible force weighing over a metric ton caused by, well, a simple oversight in fluid dynamics.
And that is the reality of physical site work. The theoretical plant designs always look flawless on paper.
Oh, yeah, always.
But the moment water actually starts flowing through the pipes, you are dealing with uncompromising physics.
Which is exactly why we are focusing on genuine, on-the-ground reality today. So for you, the South African engineers, the technicians, the people actually buying, installing, and troubleshooting this equipment, welcome to today's deep dive.
Glad to be here.
We are looking at a stack of incredibly practical, no-nonsense technical articles sourced straight from the knowledge base on the DWT website.
Yeah, and the DWT knowledge base really stands out here because it anchors everything in measurable metrics.
Right. Our mission today isn't theoretical hype. It is about the actual hardware that dictates flow, prevents those catastrophic vessel implosions, and keeps systems running safely even when you get dropped into stage 4 load shedding.
Exactly. We're looking at the specific pressure differentials, the exact cycle timings, and the subtle component choices that dictate whether a treatment plant functions for a decade or just destroys itself on the first day.
So let's start with the component that controls everything else. Before we can talk about protecting a system, we have to understand the brain directing the flow.
Right. We are talking about the multiport valve.
Yeah. Decades ago, running a media filter meant wrestling with a massive manual manifold of like 5 or 6 different hand valves.
Oh, those were a nightmare. The sequencing was entirely dependent on the operator opening and closing specific lines in a very strict order.
And the human error rate on those old manual manifolds was just staggering, right?
Completely staggering. You turn the wrong handle, and suddenly you send dirty backwash water straight into the final supply line.
Or worse, you did hit a feed pump.
Exactly. So the multiport valve replaces that entire maze. It's a single rotary unit sitting on top of the vessel or, side-mounted on larger industrial setups, handling all of that routing internally.
I always think of it as a complex railway switchyard. Water enters the valve, and internally, the ceramic discs or pistons are constantly shifting the tracks.
That's a great analogy. They reroute the raw water down one of 5 possible paths.
Right. You have the inlet, the outlet, the riser tube running down the center of the media bed, the drain line, and if it's a softener, the brine line.
Yeah, and the brilliance is in how it sequences those distinct paths to maintain the media. Consider the basic filter cycle, for example.
Okay, so it always starts in the service position, right? That's the default.
Exactly. Raw water comes in, flows downward through the media bed where the actual filtration happens, travels back up the central riser tube, and exits to supply.
Makes sense. And every other position the valve can move into exists solely to clean and restore that media bed so it can get back to that service state.
Spot on, because eventually that bed gets completely clogged with suspended solids.
And that's when the switchyard has to change tracks to the backwash position.
Right. The valve completely reverses the flow direction. Water goes down the riser tube first, hits the bottom distributor, and then pushes upward through the media bed.
So this upward flow lifts and fluidizes the media, right? Physically scrubbing the granules against each other to strip away trapped dirt.
Yes, which is then carried out to the drain. And the critical metric from the DWT technical guidelines here is the duration.
Ah, the timing.
Yeah, a proper backwash must run dirty, and then it must run completely clear. In a standard setup, you are looking at 8 to 12 minutes to achieve that stratification and cleaning.
But you cannot just jump straight back into the service position after that, can you?
Oh, absolutely not. The media bed has been lifted and expanded. It is floating around completely unsettled.
Right, so if you instantly switch to service, the downward flow will violently compress the bed.
Exactly, and it will push a massive slug of residual dirt straight into your clean water supply, which defeats the whole purpose.
That brings in the rinse or fast rinse position.
Yes. The valve switches the flow back to the normal service direction downward through the bed, but routes the output straight to the drain instead of the supply.
Oh, I see. So this gently settles the media bed back into its compacted state and flushes out any remaining microscopic fines.
Exactly. And only when that rinse is complete does the valve return to the service position.
Okay, so that covers a standard media filter.
But the complexity ramps up significantly when we transition to water softeners, right?
It really does. A softener valve has to add two entirely new positions to handle the regenerant.
You mean the brine draw with slow rinse and the brine refill? Right. And looking at the mechanics of this, standard commercial softeners do not have dedicated brine pumps.
Wait, really? No pumps at all?
Nope. The salt water is heavy, and it's just sitting in an atmospheric tank next to a pressurized vessel.
So how does it get into the vessel?
The mechanism bridging that gap is pure fluid dynamics, specifically the Venturi effect.
Okay, so inside the softener's multiport valve, there's a built-in injector.
Yes. The valve routes a fast stream of feed water through a very narrow constriction. As the water is forced through that pinch point, its velocity spikes.
And that rapid increase in speed creates a localized drop in pressure, effectively forming a vacuum.
You've got it. That vacuum is what educts the brine, sucking it out of the salt tank, mixing it with the feed water, and drawing it into the vessel.
Wow, okay. And then it passes very slowly through the resin to allow the ion exchange process to happen.
Exactly. But that reliance on the feed water's own kinetic energy creates a massive vulnerability.
Right, because the Venturi injector is entirely dependent on the incoming municipal or booster pump pressure.
Exactly. The DWT technical notes lay out a very strict minimum metric here. That injector needs at least 1.5 bar of feed pressure to generate enough velocity to create the vacuum.
And if the pressure drops below 1.5 bar...
The Venturi simply stops sucking. The brine just stays sitting in the tank.
So when a technician gets called out because the plant is delivering hard water, they might notice the salt level in the brine tank hasn't dropped for weeks.
And they often start taking the valve apart, looking for a mechanical break. But a feed pressure below 1.5 bar isn't a mysterious control board failure.
It is a fundamental limitation of the physics.
Exactly. The brine draw physically cannot function without that kinetic energy.
Understanding that internal Venturi injector is the perfect bridge to one of the most common yet easily preventable site errors mentioned in the sources.
Oh, valve compatibility. Yeah, because the valve controls the entire chemical and physical process. Installing the wrong valve on a vessel leads to massive cascading failures.
And outwardly, filter valves and softener valves from the same product families look incredibly similar.
They do. They share the same casing, the same digital displays, and often the exact same mounting threads.
But internally, the softener valve has those extra brine ports, the complete injector assembly we just outlined, and an entirely different logic board.
Right, which creates a strict one-way compatibility rule for installers.
So taking a softener valve and installing it on a plain sand filter vessel is an expensive mistake, but it isn't catastrophic, is it?
No, not catastrophic. The valve will eventually cycle into its brine draw and brine refill positions. Since there is no brine tank attached, it will just idle.
It's drawing nothing and refilling nothing. You just waste 30 minutes of cycle time and the premium cost of the more complex valve.
Exactly, but the sand still gets properly backwashed. The catastrophic scenario is the reverse.
Taking a filter valve and installing it on an ion exchange softener vessel.
Yes. That results in what the industry calls a silent failure.
Why silent? I mean, what actually happens?
Well, the resin does its job at first, pulling calcium and magnesium out of the water until it completely exhausts its capacity.
And then the controller hits its volumetric limit and dutifully triggers a regeneration schedule.
Right. The valve backwashes the resin and then it rinses it, but the critical step is completely missing.
Because there is no brine draw. The Venturi hardware simply does not exist inside a filter valve.
Exactly. The valve's internal switchyard has no tracks leading to a brine circuit. So the exhausted resin just gets a nice wash with plain water.
Which does absolutely nothing to recharge the ion exchange sites.
Nothing at all. You end up with a highly expensive vessel full of saturated resin delivering totally hard water.
And the valve clicks through its cycles, the display looks normal, and the failure remains invisible until someone actually tests the water hardness.
Precisely. So for a technician standing in a cramped, poorly lit plant room trying to figure out what equipment they are holding, the sources provide two immediate diagnostic checks.
Okay, what's the first one?
It's a physical giveaway. You look for the nipple.
The nipple.
Yeah. Softener valves have a small barbed or threaded port protruding from the side where the brine line connects to the Venturi.
Okay. And filter valves?
Filter valves are completely smooth on that side. They lack the port entirely.
That makes it easy. What's the second check?
The product code on the data plate. Using the standard Runxen 5-digit convention, the very first digit tells the technician everything they need to know.
Oh, right. A code starting with a 5 is a filter valve. And a code starting with a 6 is a softener valve.
Yes. 5 is filter, 6 is softener. It is a foolproof identifier when the physical ports are obscured.
I do want to address a major point of confusion on site, though. Carbon filters and catalytic media vessels.
Oh, yeah, that's a big one.
Because physically, they mimic softeners perfectly. They use the same sleep of composite vessels and sit in the exact same configuration in a plant room.
Right, so it is incredibly common for installers to just assume they need a softener valve.
But that assumption leads to massive water waste, doesn't it?
Huge waste. Carbon and catalytic media function through adsorption or physical filtration. They do not undergo ion exchange.
Meaning they never need to be regenerated with a salt brine.
Exactly. No matter how much they look like a softener setup, they absolutely require a filter valve.
Because putting a softener valve on a carbon vessel means the valve will perform a phantom brine draw every single cycle.
Right. You're wasting time and flushing perfectly good water down the drain during the refill stage for no reason.
The sources do highlight one highly specialized exception to this rule, though. Systems utilizing manganese green sand.
Yes, that's the outlier. Manganese green sand requires regeneration with a chemical oxidant, typically potassium permanganate.
So to draw that liquid regenerant into the vessel, the system relies on the exact same Venturi injector hardware found in a softener valve.
Exactly. But in standard commercial treatment, the foundational rule remains solid.
If the media requires a liquid chemical regenerant, it needs a softener valve. If it just needs to be washed with water, it needs a filter valve.
Spot on. So a mismatched valve ruins the treatment chemistry, but a blind spot in fluid dynamics can physically destroy the plant.
Which brings us back to the scenario we opened with, the asymmetric threat of vacuum implosions in FRP vessels.
Yeah. The math behind these failures is just staggering. We view composite fiberglass reinforced plastic vessels as incredibly robust.
Right, they're rated for continuous internal pressures of up to 10 bar.
Yes, and that strength comes from the fiberglass filament winding. When the vessel is pressurized, those filaments are loaded in tension.
They are being stretched outward, and fiberglass has immense tensile strength.
Exactly. But the vulnerability is entirely asymmetric. A vacuum inside that vessel means the external atmosphere is pushing inward.
So the shell is loaded in buckling, and an FRP vessel has effectively zero structural rating against an inward buckling force.
Zero. Comparing it to a plastic bottle illustrates the physics perfectly.
Right. If you blow into a plastic cool drink bottle, it becomes rigid. The plastic is in tension.
But if you seal your lips over it and suck the air out, the sides instantly crumple inward.
And scaling that up to an industrial FRP tank reveals the true danger. Because a full atmospheric vacuum creates roughly 1 bar of inward pressure.
And 1 bar translates to 1 metric ton of crushing force per square meter of surface area.
A ton per square meter? That is just brutal.
It really is, and the damage mechanism is often completely hidden from the operator.
How so?
Well, long before the rigid outer fiberglass shell shows signs of ovalizing or cracking, the internal polyethylene liner distorts.
Ah, the vacuum pulls the thin liner away from the fiberglass.
Right, causing it to fold inward and delaminate. The technician looks at the vessel and sees a pristine exterior, but internally the liner is ruptured and the vessel is permanently compromised.
And these vacuums are not generated by freak industrial accidents, are they? They happen during mundane, everyday operations.
Oh, absolutely. The most frequent culprit is simply draining the tank.
If a technician opens a low drain valve to empty a closed vessel, and there is no open path for air to enter at the top to replace the water,
then that falling column of fluid pulls a massive vacuum. Downhill pipework is another classic vessel killer.
Right. If the treatment plant feeds a reservoir located at a lower elevation, the pipe acts as a giant siphon.
Yes. When the feed pumps shut down, the momentum and weight of the water dropping down the elevation continues to pull, sucking aggressively on everything upstream.
You also have thermal contraction.
Yeah. If a hot clean-in-place process is run, and the vessel is sealed while still hot, the internal fluid and air contract as they cool down, naturally generating a vacuum.
The solution to all of this is arguably the most important yet cheapest component in the plant, the vacuum breaker.
Yes. It is a tiny air admittance valve installed at the absolute highest point of the system, usually directly on the vessel inlet or the adjacent high piping.
And the mechanism is elegantly simple. It is a normally closed valve. The positive pressure of the system holds a small floater diaphragm firmly shut against an O-ring.
It just sits there during normal operation, but The millisecond the internal pressure drops even a fraction below the external atmospheric pressure.
The ambient air pushes that seal open.
Exactly. It rapidly admits air into the pipework, immediately breaking the vacuum before the inward force can build.
And the moment the pressure normalizes, it instantly reseals. The operational rule is absolute here.
Absolutely. If there is any scenario where water can leave a closed FRP vessel faster than air can get in, a vacuum breaker is mandatory.
You are spending a negligible amount of money to save a 10-bar rated vessel from being structurally written off by a 1-bar vacuum.
And as the guidelines stress, it must be fitted during the initial build, because the very first time the system is drained for maintenance is exactly when the implosion will happen.
Right. So moving outward from the main vessels, the integrity of the entire plant relies on the supporting pipework components.
Yeah, solenoids, non-return valves, and relief valves. They handle the dynamic threats of overpressure, backflow, and, well, the uniquely South African variable of constant power failures.
Yes, load shedding. Solenoid valves act as the automated gates of the plant, opening and closing based on electrical signals from the controller.
And the immediate engineering question when specifying a solenoid in this country is how it behaves during load shedding. When the grid drops, what state must that valve default to?
You are choosing between normally closed and normally open.
Right. A normally closed, or NC valve, requires electrical power to lift the seal. When power is lost, a heavy spring forces the valve shut, stopping the flow.
Which is the fail-safe default for most supply lines.
Exactly. But a normally open, or NO valve, requires power to force the seal shut. When power drops, it springs open.
Ah, so you deploy these in scenarios where flow must continue safely during an outage, like gravity-fed emergency cooling loops.
Spot on. But the sources point out a critical mechanical trap when selecting these valves. Installers often ignore the difference between a pilot-operated solenoid and a direct-acting solenoid.
And that results in valves that violently stutter or just refuse to close, right?
Yeah. Most general-purpose commercial solenoids are pilot-operated because it allows a small electrical coil to control a massive volume of water.
Because the magnetic coil doesn't physically lift the heavy main rubber diaphragm.
Exactly. Instead, it opens a tiny pilot hole in the center of the valve. This allows the upstream water pressure to enter a chamber above the main diaphragm, using the water's own force to push the seal firmly closed.
So the valve is effectively using the system pressure to do the heavy mechanical lifting.
Right, but that design requires a minimum pressure differential to function. The water pushing on the diaphragm needs to be at least 0.3 bar stronger than the water resisting it.
So if you install a pilot-operated valve on a low-pressure line, like a gravity feed from roof tank, it will not have that 0.3 bar differential.
And the valve will just hunt. The diaphragm will flutter endlessly in the current, failing to create a seal.
That makes total sense. So in any low pressure or gravity scenario, the technician must specify a direct acting solenoid.
Yes, where the electromagnetic coil is mechanically linked to the main seal, pulling it open or closed entirely independent of fluid pressure.
Flow control also requires strict directional management. Non-return valves, or check valves, ensure water only moves forward.
Right, and the engineering notes outline several non-negotiable locations for these. Every single chemical injection point requires one.
To prevent the mainline pressure from destroying the dosing pump. Right?
Exactly. And to stop the doser from siphoning into the line when the system is off, pump discharges are another mandatory location, particularly when pumps are installed in parallel.
Because if two booster pumps are manifolded together and one shuts down, the live pump will push high-pressure water backward through the idle pump.
Which causes violent backspin, mechanically destroying the idle pump's impellers. You also need them on borehole risers.
And from a compliance standpoint, robust backflow prevention is required where the plant meets the municipal connection, isn't it?
Absolutely. A chemical treatment plant cannot risk a sudden drop in city pressure siphoning treated water back into the public grid.
The real diagnostic challenge with check valves is how they fail, though. When debris catches in the seal, it might only hold the valve open by a fraction of a millimeter.
Right. It doesn't present as a broken valve. It creates ghost symptoms across the plant. And the symptoms always point somewhere else.
Like a softener vessel draining dry overnight for seemingly no reason.
Or a dosing pump that constantly loses its prime despite perfect tubing. Or a booster pump that struggles to start because the casing is flooded with back pressure.
So when fluid dynamics begin behaving impossibly, the technician's first diagnostic step is to trace the line backward and inspect the nearest check valve for fouling.
Always. Finally, we have to look at pressure relief valves. These components protect whatever cannot protect itself.
Right, by opening at a predetermined set point to discharge fluid and relieve strain.
They are an absolute necessity on any line utilizing a positive displacement pump, such as a metering or chemical dosing pump.
Because centrifugal pumps will slip. If you close a valve downstream, the impeller will just spin harmlessly in the water.
Exactly. But a positive displacement pump physically forces a set volume of liquid into the pipe with every single stroke. It does not slip.
So if a valve downstream is closed, a scenario known as deadheading, that metering pump will continue to cram fluid into the sealed pipe.
And the pressure will build exponentially until the weakest point fails. The pump casing cracks, the PVC pipe shatters, or a fitting violently blows off.
The relief valve gives that expanding pressure an engineered escape route, but the installation dictates its usefulness.
This is a huge point. If a technician hard plumbs the relief discharge deep into a floor drain when no one can see it, the valve might be popping open constantly.
It saves the pipework, but it hides the fact that a severe overpressure condition is occurring upstream.
Exactly. The discharge must be plumbed somewhere highly visible so the plant operator immediately knows the system is fighting a blockage.
Building a resilient water treatment plant requires zooming in on these granular details. It is about understanding that a backwash requires exactly 8 to 12 minutes to stratify the media bed.
It is ensuring the feed pumps deliver that critical 1.5 bar of pressure so the Venturi injector can actually draw the brine.
It is checking the Runxen data plate for a 6-foot code to guarantee the resin vessel actually has a brine circuit.
And it is about deploying an inexpensive vacuum breaker to protect a massive 10-bar rated asset from a 1-bar atmospheric crush.
All of these technical guidelines, cycle charts, and diagnostic steps live permanently in the knowledge base on the DWT website. They are there for you to reference on your phone the next time you are standing in a plant room tracing a fault.
Yeah, understanding these forces fundamentally changes how you look at a site. The hardware doesn't exist in isolation. It is constantly interacting with the environment.
Which brings up a final thought to consider on your next installation. We discussed how a falling column of water inside a plant can pull a vacuum and destroy a vessel.
Yes.
Now consider how those exact same principles apply to the municipal mains feeding your facility outside.
Oh, that's a brilliant point.
When the municipality shuts off the water and the massive city grid begins to drain, that entire underground network becomes a rapidly expanding vacuum.
Right, and if your incoming non-return valves are fouled, your plant isn't just sitting idle waiting for the water to return.
It becomes the supply. And the city grid becomes the vacuum pulling forcefully on every piece of equipment you've just installed.
That is a terrifying thought for any installer.
It really is. Until next time, keep analyzing the flow and stay safe on site.